So we talked a little bit about graphs and how we can explore the limit of a function that we have a graph for by checking to see if the limit from one direction is the same as the limit from the other direction. And even if that one point right there isn't filled in or is somewhere else, as long as the graph was approaching the same place from both directions, we have the limit at that place where they were going to meet. We want to start to talk now in section 2.2 about expanding that idea and not just thinking about letting x approach some number, but thinking about the far edge of a graph. So what happens to our function value, our y, as x gets super big, as x moves toward infinity, or as x moves toward negative infinity? So this is a graph of f of x is 1 over x. You probably have it already graphed in your functions booklet. You could practice plotting some points. You could use a grapher to graph it. You might just remember what this looks like. But we need to understand why this graph has this shape. So notice that as I see the point 1 comma 1, because when x is 1, then we have 1 over 1, which just makes 1. What about when x is 2? My denominator is going to be 2. I have 1 over 2. That's going to be a half, which is actually smaller than 1. And then as x gets bigger and bigger from here, I can imagine that that denominator is getting bigger and bigger, which means the value of my fraction is actually less and less, which means that my y value is going to tend closer and closer and closer to 0. So you can imagine doing that infinitely many times. You're going to have to do it infinitely many times if you want to get as close to 0 as possible. You're never actually going to get there. What happens if I still want my x to be positive, but I let the denominator get smaller and smaller towards 0? Well, as I divide by a smaller and smaller number, the result is actually bigger. So that's why as x gets closer to 0, at least from this direction, my y values get bigger and bigger. So what I really want to focus on is what happens as I let x get bigger and bigger. So if I imagine the right-hand edge of my graph, doesn't matter how big a denominator I make here, 1 over some big number is still a positive number. It's just going to get closer and closer to 0. So you've drawn these in. That's 1 comma 1, gets closer to 0 there, gets closer to the axis there. Your picture is going to be neater. So I've asked you to investigate what happens as x goes toward infinity, the limit as x goes toward infinity. What's happening to the y value? Well, the y value is getting closer and closer and closer to 0. So this limit equals 0. Is the graph ever going to touch a place where y equals 0? No, but that's where it's headed. What about the limit as x goes toward negative infinity? So that means I'm going to follow the graph as far as I can go to the left-hand side. And this time I'm going to have a output that's negative because I'm going to have a positive 1 divided by a negative denominator. It's still going to be a negative result, but it's going to get closer and closer to 0 because, again, that denominator's, the size of the denominator is increasing. So this limit is also 0. The limit as x goes toward negative infinity. This next one, I've asked you to investigate this function that is not in your function booklet. Maybe you've never even seen it before. So I'm going to suggest you have this in your back pocket. I've got a screenshot here I'm going to open up from Desmos. So you can see I typed that function into Desmos, y equals 2x minus 1 over x plus 3. Word to the y's, you need to put the parentheses around the numerator for sure. And on the calculators we use in class, you would need to put the parentheses around the denominator as well, or you won't get the right picture. So now I've asked you to investigate the behavior of this function, the limit of the function, which means the y value of the function, as x gets really, really, really big. So I can imagine following this line along here. If you're really careful about reading this graph, that's 1, 2, 3, 4, 5 spaces to get up to 10. So that means I'm counting by 2s. This graph kind of levels out at that first silver bar. So this seems to be approaching the value of 2. And as I follow along here the other direction, I also seem to have a limit of 2. The y value is getting closer and closer and closer to 2. It's not ever going to get there. If you wanted to think about why that's happening, you could imagine plugging in a really big number for x. So if x was 1,000,000, then your numerator would be 2,000,000 minus 1, and your denominator is going to be 1,000,000 plus 3, which, if you wanted to like calculate it out, is really, really, really close to 2. So that's our limit in this case. So if you just explored a function whose you've probably never seen before, but now you've thought about its limit by following the graph. You've thought about the limit as x approaches infinity by following the graph all the way to the right, and the limit as x approaches negative infinity by following the graph all the way to the left. All right, so this is a big idea. Each of these graphs has what we call a horizontal asymptote, a line, in this case a horizontal line, that your graph gets closer and closer and closer to, but never crosses or touches. And in fact, your graph approaches that horizontal asymptote once all the way at the right edge of the graph and once all the way at the left. So a horizontal asymptote, which I'm sure you've graphed in when you talked about rational functions in pre-calculus, it actually has the real definition for when there's an asymptote, a horizontal asymptote, comes from an understanding of limit. If there is a number that your graph is getting closer and closer and closer to out at one of its far edges, then, well, that's exactly what limit notation is for. So this is a big deal. You very well might find there's a question about this on your test, your AP test. There is a horizontal asymptote in the function, in the graph of the function f of x, if the limit as x approaches infinity of f of x is b, or the limit as x approaches negative infinity of f of x is b. And your the notes paper makes it slightly more clear than this slide here. The equation for that asymptote is y equals b. So if, as x gets super big, the y values get closer and closer and closer and closer to 2, for example, like in the second graph, then we say there's a horizontal asymptote at y equals 2, because the limit as x approaches infinity of 2x minus 1 over x plus 3 equals 2.